This segment is about the analysis of variance, or ANOVA table. The total sums of squares can be partitioned into two components, into the sums of squares explained by regression and the sums of squares that are left over, error sums of squares or residual sums of squares. The total sums of squares are as usual here. The residual sums of squares, well, are the sum over the residuals. This is one residual squared. Yeah. And then it turns out that the term left in here is the model sums of squares, where y hat is the predicted value, and this is the average. If you think of y hat as the predicted average, then you can say how much does the model improve over the generic average y bar, get to a better average conditional on x. And it turns out that the degrees of freedom can also be partitioned. Here we have n-1 degrees of freedom because we have to estimate the mean, the overall mean. We're losing one parameter. So we have n-1 degrees of freedom. We're losing 1 degree of freedom. Here for the residuals, we know that we lose p plus 1 degree of freedom because we have beta, well, that many betas. So p betas and then beta 0. And here we have p degrees of freedom. And those just sum together nicely. So why do I have p degrees of freedom? Well, I have p plus 1 parameters, but I'm losing one parameter here in estimating the grand mean. This decomposition, this ANOVA decomposition, we will not prove that, but I will outline where the proof is going. We're doing an arrow subtraction. So by that, I mean we add something and we subtract something. So in the end, we have added 0. And you will see that this part and that part corresponds to these parts over here. Well, a plus b squared is a squared plus b squared plus 2ab. And the first two parts correspond exactly to what we need. So that means if this holds, then this last part must be 0, and it is. And to show that this is 0, we have to use two properties that we have not seen before, but which are true. And one is that the average residual is 0. Well, if the average residual is 0, then it's also the total residual is 0. So remember that residuals above the line are positive, below the line are negative. We're trying to find the best line. And it turns out that when you sum all those residuals, the positives and the negatives cancel out and are 0. And then we have this second equality that also holds. In the output, we have an ANOVA table right here, highlighted in red. The model sums of squares and the residual sums of squares sum to the total sums of squares. The model degrees of freedom and the residual degrees of freedom sum to the total degrees of freedom. We can compute the mean squared errors by dividing the model sums of squares with the respective degrees of freedom, and likewise for the residual sums of squares, and also for the total sums of squares if you want. These two numbers do not add up to this one here. This number is the estimate of sigma squared. Okay, and in R, we get the exact same table. In R, you have to specify that you want it, ANOVA, and then the model. And then you get the exact same table. Okay. Why do we want ANOVAs? Well, this particular ANOVA decompositioned the total sums of squares into two components, the model and the error. In general, you can break the model sums of squares down even further so that instead of two components, you have more than two components. And we will see that the subcomponents correspond to individual variables or groups of variables. And when we want to test several parameters simultaneously, we will need to test whether additional sums of squares due to those parameters are large in some sense. So large that they're not consistent with zero. And this is called the extra sums of square principle. That's going to be in the next segment, but for now, this is the end.